We have a few more pieces to put together to be able to graph polynomials, but we're getting pretty close based on the knowledge that we have from algebra. There are some limitations in our knowledge, but without calculus, but we can do a pretty good job with our algebra knowledge. So let's take a look. First, always, whenever we're trying to graph anything, we want to know the y-intercept of that function. So that's our third thing we're looking at to graph this polynomial. We know that we're looking at finding p of 0, or in this case, f of 0. So f of 0 is 0 to the 4th minus 4 times 0 squared plus 4, which equals 4. So our y-intercept is 0, 4. So that would help us, that would give us another point on the polynomial to help us graph it. One last little thing, just a quick thing. Turning points of a polynomial are points where the function changes from increasing to decreasing or from decreasing to increasing. We kind of defined that earlier as the minimum, the local minimums or maximums. So that in this picture down here would be here, it changes from increasing to decreasing, here from decreasing to increasing, here from increasing to decreasing, and here. So this has 4 turning points, just based on the definition of a turning point. The second question in this example is, what is the degree of the polynomial? We need this fact in this box above here to answer that. If a polynomial f of x has degree n, then, oopsie, that should be a then, the graph of f has at most n minus 1 turning points. So if it has n minus 1 turning points, the degree has to be 1 more than that at least. So this could have degree equal to 5. You also could notice here that this function has 1, 2, 3, 4, 5 x-intercepts. So it has to have degree at least 5. It could have a higher degree than that because notice it says, let's say for example, if the polynomial has degree 6, then it has at most 5 turning points. So it could have less turning points, but 5 would be the most if the degree was 6. The problem here is that this can't have degree 6 because if it did, one of these x-intercepts would have to have multiplicity of 2, right? So if we had degree 6, let's write that down for a second. That means with these 5 x-intercepts, that 6th one has to come from somewhere. So when you add up all the multiplicities, it has to add up to the degree. If you have you could have some imaginary ones in there, but in this case, with this many real zeros, these 5 zeros, it would have to have one of them have multiplicity 2. But none of these have multiplicity 2 because they all cross. The graph crosses at all of these x-intercepts. There's none of that touching and turning around and coming back. So there can't be an even multiplicity 0. You could have 7 for your degree because, say, one of these could have multiplicity of 3. Okay, 9, 11, and so on. You could go on with all those those odd degrees. Just a little extra thing to help you kind of make sure you understand what polynomials look like. We're going to put all of this information together to graph these polynomials. This was sort of the goal of this part of these notes, was to help us graph polynomials. First, we're going to determine the end behavior using that leading term test. Then we're going to find the zeros because those will give us the x-intercepts of the graph. Using the multiplicity of those, we can figure out what's happening at the intercepts, find the y-intercept, maximum number of turning points. Sometimes symmetry, using the idea of even and odd functions, is helpful for these because then you only have to look at half the picture and you get the other half based on the symmetry. It's going to be critical at this point that you also plot some additional points between the zeros. We'll talk about that when we get to that point where we're like, oh, what do? I need some more information here. Let's start with the end behavior, that leading term test. Remember, for that, we need to know degree. So this would be step 1 above there. The degree and the leading coefficient, which in this case is 1. I have odd degree and positive leading coefficient. Odd degree means they go opposite directions. Positive leading coefficient means it goes up to the right and down to the left. I just drew a little squiggle in the middle because we don't know what's happening from in the middle there. That doesn't help us at this point put anything on the actual graph. We need more information. Let's work on the zeros. That comes from where the function is equal to 0. I think the easiest way to find that is to factor out an x. Let me give you a little warning here. Sometimes with this, students are tempted to add x over and then divide both sides by x to give you 1 equals x squared and then x equals plus or minus 1. The problem with that is that you lose a 0 when you set, if you notice when you actually solve this, you get x equals 0, x equals 1, and x equals -1. This way, if you do this where you divide by the x, you have only found x equals +1 and -1. The reason for that is because when you do this step of dividing both sides by x, you are assuming that x is not 0. When in reality, x can be 0 and is indeed 0 to make this a true statement. So we don't want to make that assumption. So do not do that. I've seen students do it a lot, so that's why I wanted to mention it to you. We have 3 zeros here. X equals 0. Let me actually just organize these in a table to help us. I'm going to put them in order, -1, 0, and 1. Let's talk about the multiplicity of each because we care about that because it tells us the behavior. So we are still on step 2 listed above there. The multiplicity of each of these is just 1. I have x to the first that gave me x equals 0. I have x minus 1 to the first, which gave me x equals 1. And I have x plus 1 to the first power, which gave me this x equals -1. Which means this graph crosses at each of these. Let's do this. Okay, we can plot those points at this point. These are x-intercepts on the x-axis. I have my origin. I'm going to make my scale a little bigger here along the x-axis. I'm going to call this 1 and this -1. So I'm kind of going by, this scale is like 1/4. Each of these marks is a 1/4. Okay. That's step 2. Step 3, I'm going to erase this work here of what not to do. So I have a little more space. Step 3, finding the y-intercept means find f of 0, which is just 0, which we already knew. Oops, I forgot to plot these points, didn't I? We already knew because we had the x-intercept of 0, 0. Fourth step up here, determine the maximum number of turning points. Max turning points will be 2 because the degree is 3, so it's going to be 1 less than that. And I think I need some additional points here. I need to know what's happening. I do know that this function is crossing at each of these zeros. I also know on the right end, it is going up from this 0. There are no other zeros, so it can't come back down and go up from a different 0. I know it's crossing at that 0. It's going to come down to some point, reach a minimum, come back up and cross this way. It has to cross here, come up, reach a maximum, cross here, and then from here it's going to go down based on my first step here, right? Based on this that I found here. It goes up on the right and down on the left. So from the rightmost 0, I can go up. From the leftmost 0, I can go down. That's not a guarantee, but especially based on, if this is a bigger number, but it's a good guideline. At this point, we are doing the best we can without some calculus. What I'm going to do for some extra points is just set up a table of values here. I'd like to know what's happening. How low does that go? That's why I didn't really graph this. I don't know how far down I go between that 0 and 1. So I want to plug in 1/2. Bless you. I want to plug in negative 1/2 into this function. Plugging in 1/2, I get 1/2 cubed would be 1/8. Minus 1/2 would be negative 1/4. If I get a common denominator there, 1/8 minus, oh no, I'm sorry, it's negative 3/8. Trying to do that in my head. Maybe I should actually write it. That is usually a good plan. 1/8 minus 4/8 would be negative 3/8. So it actually does not come down very far. I'm going to do the same scale on my y-axis that I did on my x-axis. 2, 3, 4. So I'm down here at negative 1. Negative 2. If I did not get a negative number here, I did something wrong. Negative 3/8. Let's see, halfway would be negative 4/8. So we're going to go here, halfway between these two. This is 1/2, right? That's what I plugged in. So it doesn't come down super far here. So that kind of matches up with what I had there. When I plug in negative 1/2 to find how high it goes up, I get negative 1/8 minus negative 1/2, which would be plus 1/2. Negative 1/8 plus 4/8. Will be 3/8. So we're going to do the same thing. This is a 1, so 3/8. This is half, which would be 4/8. So I'm going to be here for that halfway point. I do not know that that's actually where that maximum is. Kind of guessing that it's halfway in between the zeros, which is a terrible guess. But it's the best I can do for now. For those of you taking calculus, stay tuned. You will see how to exactly find that maximum in a minute. Where exactly is that function? Because we're kind of making an assumption that it's halfway in between the zeros there. Okay, that's our graph of x cubed minus x, at least the best we can do for now. I like it, using the information that we have. Let's do one more of those graphing examples. Okay, we're going to start with step 1. We need the degree and we need the leading coefficient. So first, the degree of this is 4. You may be wondering why. The degree comes when it's all multiplied out, not when it's in factored form. If I multiplied all of this out, I have an x minus 2. I'm going to multiply that by an x plus 1, another x plus 1, and an x minus 1. All of those are going to multiply out to give me an x to the 4th. I'm also going to have that negative 1/2 in front there, and then some other stuff of lower degree. When I distribute everything out, there will be smaller degree terms. My leading coefficient is negative 1/2. That tells me end behavior. Even degree means they both go the same way. Think of a parabola. This is not a parabola, it's degree 4 instead of degree 2, but just that's how I remember that. The fact that they're both negative, or I'm sorry, the leading coefficient is negative means they both go down. So that's our end behavior. Second step, find the zeros. Fortunately, this is already in factored form, which is an important key to note at this point. We are setting the factors equal to 0 to find these zeros. X equals 2, x equals negative 1, and x equals 1. Zeros are, I'm going to put them in numerical order, negative 1, 1, and 2, just because I think left to right. Multiplicity, negative 1 came from this x plus 1, so it has multiplicity 2. X equals 1 came from the last term here. It has multiplicity of 1, and x equals 2 has multiplicity of 1. The behavior here is this one just touches and turns around. These two, it's going to cross. Let's find the y-intercept and then we'll start plotting some points. Y-intercept, plug in 0, f of 0. Let me zoom out a little bit here so I can see this all on one page. F of 0 is negative 1/2 times 0 minus 2 times 0 plus 1 squared times 0 minus 1. Negative 1/2 times negative 2 times 1 times negative 1 is going to be negative 1. So my y-intercept is the point 0, negative 1. This is another one where the numbers are all pretty small, right? The zeros are negative 1, 1, and 2. My y-intercept is negative 1. Because of that, I am going to make the same scale that I made on the previous example. Where this is 1 and this is 2. Negative 1, negative 2. This is 2. Okay. So the end behavior kind of comes in at the end as an important key there. So I'm going to wait on that. Let's plot the points that we know. We know we have a y-intercept at 0, negative 1. I'm going to grab another color here just so it's a little easier to see. 0, negative 1 would be here. That's our y-intercept. We have x-intercepts at negative 1, 0, 1, 0, and 2, 0. Here, here, and here. Now we have those points, and that's pretty much it. Oh, goodness, excuse me. We do have other information, but let's talk about what else we have. We know in step 4 we have turning points of at most 3 or less. Okay, that's our maximum turning points is 3. And then we'll do some extra points as we need them in our 5th step there. Here's what I know. I know to the right, from the end of this, it is going to go down. Because I have no additional x-intercepts, it has to go down from here. And it could have like a, this kind of thing where it doesn't cross the axis. But because we have this limit of 3 turning points, we know that can't really happen with these 3 zeros being where they are. So we couldn't really have something like that. So it's safe to say from here, it's going to go down to negative infinity based on that end behavior discussion. Same thing from the leftmost 0 here, -1, it's going to go down. Now I'm going to use the behavior of the zeros to tell me what's happening in the middle. At -1, it touches and turns around and comes back. So it's going to do this. And I already have a point here to come down to. I don't know that that's the minimum, but for now, that's the best I can do, is to hope that that's the minimum. And come back up to that second x-intercept where it crosses, goes up. I also know it crosses at 2. What I don't know is how high it goes between 1 and 2. So I need some more information because I don't know if I want to do this or if I want to do this or way higher, right? So that's why I need some more information. And I'm going to plug in, I'm going to plug in 1.5 into this function, f of 3/2. I think it's easier as a fraction. -1/2. 3/2 minus 2 is also -1/2. 3/2 plus 1 would be 5/2, and I need to square that. 3/2 minus 1 would be 1/2. I'm thinking of all of those fractions, the 1s as 2/2, and the 2 is 4/2. So that's where I got those numbers from. -1/2 times -1/2 times 25/4 times 1/2, which is a nice round number of 25 over, let's see, 4 over 32. 2 times 2 times 4 is 16, times 2 again is 32. And it's positive, which is what I expected. So one thing to think about, 24 over 32, both of those are divisible by 8. And it gives me 3/4. So this is just a tiny little bit more than 3/4. 1.5 would be here. So we're a little tiny bit more than 3/4. So we're going to come up, hit that point, and then come back down. Remember, polynomials are nice and smooth curves, no sharp turns. So this is what we get. Again, we don't know exactly what's happening between -1 and 1 and what's happening between 1 and 2, but we're doing the best we can by picking a number right in the middle of those. That's graphing polynomials. The problem that we have here is that we have only been able to do this with something that is either already factored or can be factored easily with techniques that we already know, which means factoring by grouping, that means polynomials of the quadratic type, something that we know how to factor. But there are lots of polynomials that we do not yet know how to factor. That's where we're going next.